Hello there, and welcome to the Sleepy Science Channel. Tonight we'll be exploring the fascinating world of flight, from the earliest dreams of soaring like birds to the magnificent machines that carry us through the clouds today. Above us, at this very moment, thousands of aircraft trace invisible paths across the sky, each one a marvel of engineering, carrying people toward distant horizons. The story of flight is one of human imagination, of dreams that refused to stay grounded, of courage and innovation that transformed the impossible into the everyday. If you enjoy these quiet explorations, I invite you to like and subscribe or share a simple thought down in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is rest, settle in, and allow the gentle hum of aviation history to carry you into peaceful slumber. Let's begin. The dream of flight. Humans have dreamed of flight for thousands of years. Long before the first airplane ever lifted from the ground, people gazed at birds with wonder and longing. Ancient myths from every culture tell of humans taking to the sky. The Greek tale of Icarus, who flew too close to the sun with wings of feathers and wax. Chinese legends of flying chariots and magical carpets. Indigenous peoples across the world watched eagles soar and imagined themselves among the clouds. This dream was universal, written into the human heart. For millennia, flight remained fantasy, something reserved for gods and mythical creatures. Yet the desire never faded. Artists sketched impossible machines. Inventors built contraptions that failed spectacularly. Still, generation after generation kept looking upward, kept dreaming, kept believing that one day humans would join the birds in the endless blue. Leonardo da Vinci sketched flying machines in the 1500s. In Renaissance Italy, a brilliant mind turned its attention skyward. Leonardo da Vinci, painter, inventor, and visionary, filled notebooks with careful drawings of flying machines. His sketches showed ornithopters, devices with flapping wings meant to mimic birds. He studied the anatomy of bird wings, measuring angles and movements with scientific precision. He designed parachutes, helicopters, and gliders, all centuries before the technology existed to build them. Though none of his flying machines were constructed in his lifetime, his notebooks revealed a profound understanding of the principles that would one day make flight possible. Leonardo recognized that human muscle power alone would never be enough for sustained flight, that the key lay in understanding how air moves around wings. His sketches were not idle fantasies, but serious attempts to solve one of humanity's oldest puzzles. When his notebooks were rediscovered centuries later, aviation pioneers found inspiration in his detailed observations and elegant designs. The first successful flight lasted only 12 seconds. On a cold December morning in 1903, on the windy dunes of Kitty Hawk, North Carolina, two brothers from Ohio achieved what had eluded humanity for millennia. Orville and Wilbur Wright, bicycle mechanics with no formal engineering training, launched their fragile aircraft into the wind. That first flight covered just 120 feet, staying airborne for only 12 seconds. It was shorter than the wingspan of a modern jumbo jet. Yet, in those 12 seconds, everything changed. The Wright brothers had not simply built a machine that could leave the ground. Many had done that. They had built a machine that could be controlled in the air, that responded to the pilot's commands, that could be steered and balanced. This was the crucial breakthrough. Within hours, they made 3 more flights that day, the longest lasting 59 seconds and covering 852 feet. When they returned to their workshop, they knew they had opened a door that would never close. The age of flight had begun. The Wright brothers were bicycle mechanics, not trained engineers. What the Wright brothers accomplished is even more remarkable when you consider their background. They had not attended university. They had no degrees in physics or mathematics. They ran a modest bicycle shop in Dayton, Ohio, repairing and selling bikes to local customers. But they possessed something perhaps more valuable than formal education: insatiable curiosity and methodical patience. They read everything they could find about earlier attempts at flight. They wrote to experts, asking questions. They built a wind tunnel in their shop to test wing designs, conducting thousands of experiments. They learned that much of the accepted wisdom about flight was simply wrong. Where others had failed through reckless trial and error, the Wright brothers succeeded through careful observation and systematic testing. They understood that flight required solving not one problem, but three: lift, control, and propulsion. Their background in bicycles actually helped, as controlling a bicycle requires similar balance and coordination to controlling an aircraft. They proved that genius does not require credentials, only dedication and the courage to challenge what everyone else assumes is impossible. Early pilots flew without instruments, navigating by sight alone. Imagine climbing into an open cockpit, the wind whipping against your face, with nothing but your eyes to guide you. The earliest pilots had no altimeters to tell them how high they were flying, no airspeed indicators, no compasses or radios. They flew by the seat of their pants, literally, feeling the vibrations of the aircraft through the wooden seat, judging speed by how the wind felt, estimating altitude by looking down at the ground. Navigation meant following roads, railways, and rivers, landmarks visible from the air. Getting lost was common. Running out of fuel was a constant worry. Weather could appear suddenly, and with no instruments, pilots had to rely entirely on what they could see and feel. Landing meant finding a suitable field and hoping it was smooth enough. These pilots were not reckless daredevils, though many were brave beyond measure. They were explorers of a new frontier, learning through experience what could and could not be done. Each flight added to the collective knowledge of aviation, building the foundation for all that would follow. The first airplane carried no passengers, only the pilot. When the Wright Flyer lifted off the sands of Kitty Hawk, it carried only one person, the pilot lying prone across the lower wing, controlling the aircraft with levers and hip movements. There was no room for passengers, no cargo hold, barely enough space for one human being and the engine. The entire aircraft weighed only 600 pounds. Its engine, built by hand in the Wright brothers' shop, produced just 12 horsepower, less powerful than many modern lawnmowers. The pilot could not sit upright but had to lie flat to reduce air resistance. This first aeroplane was not a vehicle for transportation, but a proof of concept, a demonstration that controlled, powered flight was possible. It would take years before aircraft could carry passengers or cargo, years of refinement and redesign, of stronger engines and more efficient wings. But that first flight, carrying only a single brave soul, proved that the dream was real, that humans could fly. Flying was extremely dangerous in the early days. Aviation's pioneers knew they were risking their lives every time they climbed into their fragile machines. Engines failed frequently. Wings broke under stress. Pilots crashed into trees, buildings, and the ground. There were no safety regulations, no training programs, no emergency procedures. You learned to fly by flying, and many paid for their education with their lives. Harriet Quimby, the first American woman to earn a pilot's license, died when she was thrown from her aircraft during a routine flight. Eugene Ely, who made the first landing on a ship, died in a crash at an air show. The list of early aviators who perished is long and sobering. Yet, despite the danger, people kept flying. They knew they were building something important, creating a new form of transportation that would one day be commonplace. The risks they took, the courage they showed, paved the way for the safe, reliable air travel we know today. Every safety feature on modern aircraft, every regulation and procedure grew from lessons learned through tragedy and sacrifice. The first flight across the English Channel thrilled the world. In 1909, just 6 years after the Wright brothers' first flight, a French aviator named Louis Blériot accomplished something that captured global attention. He flew across the English Channel from France to England, a distance of about 22 miles over open water. The flight took 37 minutes in a small monoplane with an engine that barely kept running. The crossing was perilous, with no way to land if the engine failed, and no rescue if he crashed into the cold water below. Blériot navigated by compass and instinct, flying through fog and dealing with engine overheating. When he finally spotted the white cliffs of Dover and landed in a field near Dover Castle, he became an international celebrity overnight. His achievement proved that aircraft could be used for practical travel, that they were not merely fairground curiosities. Newspapers around the world declared that Britain was no longer an isolated island, that the age of aerial communication had arrived. Military strategists immediately understood the implications. The channel that had protected England for centuries could now be crossed in minutes. Airmail began carrying letters across vast distances faster than trains. Before email, before telephones became ubiquitous, letters were the primary form of long-distance communication, and getting mail from one place to another quickly was a challenge. Early experiments with airmail began in the 1910s, with pilots carrying sacks of letters on experimental routes. The service was unreliable at first, with frequent crashes and lost mail, but the speed was revolutionary. A letter that would take days or weeks by train could be delivered in hours by air. By the 1920s, regular airmail routes crisscrossed America and Europe. Pilots flew through darkness, storms, and fog to deliver their precious cargo. They followed lines of bonfires lit along the routes, primitive navigation beacons to guide them through the night. Airmail pilots were among aviation's greatest heroes, flying dangerous routes in all weather, pioneering the paths that would become the airways of modern aviation. The airmail service became the foundation for commercial aviation, proving that aircraft could provide reliable, scheduled service. Charles Lindbergh flew solo across the Atlantic, capturing the world's imagination. On May 20th, 1927, a young airmail pilot from Minnesota climbed into a small, cramped aircraft called the Spirit of St. Louis and took off from New York, heading east across the Atlantic Ocean. Charles Lindbergh was 25 years old, relatively unknown, attempting what many thought was suicide. The Atlantic had claimed several lives already, pilots who tried to cross and never arrived. Lindbergh flew alone, with no radio, no co-pilot, fighting exhaustion and hallucinations during the 33.5-hour flight. He carried sandwiches and a canteen of water. He had to stay awake, remain alert, navigate by compass and stars. When he finally landed at Le Bourget Field outside Paris, he was greeted by a crowd of over 100,000 people who had heard about his attempt and waited through the night. His achievement made him one of the most famous people in the world overnight. More importantly, it proved that long-distance air travel was feasible, that aircraft could span continents and oceans, connecting the world in ways previously unimaginable. Amelia Earhart became the first woman to fly solo across the Atlantic Ocean. 5 years after Lindbergh's famous flight, Amelia Earhart set her sights on the same challenge. She had already crossed the Atlantic as a passenger in 1928, but she was determined to make the journey herself as pilot in command. On May 20th, 1932, exactly 5 years after Lindbergh's departure, Earhart took off from Newfoundland in a red Lockheed Vega. She faced terrible weather, equipment failures, and ice forming on the wings. Her altimeter failed, leaving her unsure of her height above the ocean. Flames shot from a cracked exhaust manifold. Despite everything going wrong, she pressed on, finally landing in a pasture in Northern Ireland after nearly 15 hours in the air. She became an international icon, proof that women could accomplish anything men could in the new field of aviation. Earhart continued pushing boundaries until her mysterious disappearance in 1937 while attempting to fly around the world. Her legacy inspired generations of female pilots and adventurers. Early passenger planes were loud, cold, and uncomfortable. When commercial aviation began carrying passengers in the 1920s and 1930s, flying was nothing like the experience we know today. Aircraft were small, holding perhaps 10 or 12 passengers in wicker chairs bolted to the floor. There was no soundproofing, so the roar of the engines was deafening. Passengers wore leather helmets and goggles because the cabins were not pressurized or heated. Cold air rushed through gaps around windows and doors. The ride was bumpy, with aircraft bouncing through every pocket of turbulence. There were no bathrooms on many early flights, no meal service, though some airlines handed out box lunches. Flights were slow, often stopping multiple times to refuel. A journey across the United States took more than a day with overnight stops. Yet people were willing to endure all this discomfort because flying was still faster than any alternative. It was an adventure, a glimpse of the future, worth every bump and chill. These early passengers were pioneers in their own right, trusting their lives to a technology barely a generation old. The DC-3 revolutionized commercial aviation in the 1930s. In 1935, the Douglas Aircraft Company introduced an airplane that would change everything. The DC-3, or Dakota as it was known in military service, was not the first passenger plane, but it was the first truly successful one. It could carry 21 passengers in relative comfort, fly fast enough to compete with trains, and operate profitably without government subsidies. Airlines around the world bought DC-3s, using them to establish routes across continents. The aircraft was reliable, easy to maintain, and forgiving to fly. When World War II began, the military ordered thousands of them, using them to transport troops, cargo, and wounded soldiers. DC-3s dropped paratroopers on D-Day, supplied troops across the Pacific, and served on every front. After the war, surplus military aircraft flooded the market, allowing airlines around the world to expand rapidly. Many DC-3s are still flying today, more than 80 years after they were built, a testament to their robust design. This single aircraft type did more to make air travel commonplace than perhaps any other. Planes were first used in warfare during the First World War. When war broke out in Europe in 1914, aircraft were still novelty items, barely a decade old. Military leaders initially dismissed them as toys, useful perhaps for reconnaissance but not for serious combat. The first military pilots simply flew over enemy lines, observing troop movements and reporting back. Pilots from opposing sides would sometimes wave at each other as they passed. But this gentlemanly phase did not last long. Pilots began carrying pistols, then rifles, taking shots at enemy aircraft. Soon, machine guns were mounted on planes, synchronized to fire through spinning propellers without hitting the blades. Aircraft began dropping bombs, attacking ground troops, engaging in aerial combat called dogfights. By war's end, aviation had evolved from curious experiment to essential military tool. Aces like the Red Baron became household names. The lessons learned in combat about aerodynamics, engine performance, and tactics accelerated aviation technology by decades. What began as reconnaissance evolved into a new dimension of warfare that would shape conflicts throughout the 20th century. The Red Baron became the most famous fighter pilot of the First World War. Among all the pilots who flew during the Great War, none achieved greater fame than Manfred von Richthofen, known to history as the Red Baron. He painted his aircraft bright red, making himself instantly recognizable to friend and foe alike. Richthofen was credited with 80 confirmed victories, more than any other pilot of the war. He was not reckless, but methodical, studying tactics, choosing his battles carefully, training the pilots under his command. He led a squadron known as the Flying Circus because their brightly painted aircraft seemed to travel from place to place like a carnival. The Red Baron became a legend on both sides of the conflict, respected by enemies who mourned when he was finally shot down in April 1918, just months before the war ended. He was only 25 years old. His red Fokker triplane became an enduring symbol of early aerial combat, of an era when individual skill and courage mattered more than technology, when combat in the air retained traces of medieval chivalry, even amid industrial slaughter. Biplanes had two wings, stacked one above the other. If you picture an old-fashioned aeroplane, you probably imagine a biplane, with two sets of wings, one above the other, connected by wooden struts and wire bracing. This design dominated early aviation because it provided structural strength without excessive weight. Wings need to be strong enough to support the aircraft's weight during flight, and early materials like wood, fabric, and wire were not as strong as modern alloys. Having two wings braced together created a rigid structure that could withstand the stresses of flight. The double wings also provided more lift, allowing aircraft to take off from short, rough fields. But biplanes had drawbacks too. All those struts and wires created drag, resistance that slowed the aircraft and wasted engine power. As engines became more powerful and materials improved, designers began building monoplanes, aircraft with a single wing. These were faster and more efficient, gradually replacing biplanes in commercial and military service. Yet biplanes retained a charm, a connection to aviation's romantic early days, and some are still flown today by enthusiasts who cherish their history. Fabric-covered wooden frames in the earliest aircraft. The first airplanes seem impossibly fragile to modern eyes. Their frames were built from wood, usually spruce for its combination of strength and lightness, carefully joined with glue and screws. Over this wooden skeleton, builders stretched fabric, typically linen or cotton, then painted it with dope, a coating that tightened the fabric and made it somewhat waterproof. The wings, fuselage, control surfaces, all were fabric over wood. These aircraft were delicate, vulnerable to weather, moisture, and rough handling. Fabric could tear in strong winds. Wood could rot or split, yet these materials were all that was available, and skilled craftsmen learned to build remarkably capable machines from them. The rustle of fabric in the wind, the creak of wooden joints, the smell of dope drying. These sensory experiences defined early aviation. As technology advanced, metal began replacing wood and fabric, first aluminium, then advanced alloys. But the era of fabric and wood holds a special place in aviation history, a time when airplanes were built more like musical instruments than machines, crafted by hand with care and artistry. The first jets flew near the end of the Second World War. For decades, all aircraft were powered by propellers driven by piston engines, similar to automobile engines, but larger and more powerful. These engines had natural limits to their speed and altitude. Propellers became inefficient as aircraft approached the speed of sound. In the late 1930s, engineers in Germany and Britain began experimenting with a radical new engine, the turbojet. Instead of using pistons and propellers, turbojets worked by sucking in air, compressing it, mixing it with fuel and igniting it, then expelling the hot gases out the back to create thrust. The Germans flew the first operational jet fighter, the Me-262, in 1944. The British developed the Gloucester Meteor around the same time. These aircraft were faster than anything else in the sky, but they arrived too late to change the outcome of the war. After 1945, jet technology advanced rapidly. Jets could fly higher, faster, and farther than propeller aircraft. Within 2 decades, jets had taken over military aviation and were beginning to dominate commercial aviation as well. The jet age had arrived. Breaking the sound barrier seemed impossible until 1947. As aircraft approached the speed of sound, about 760 miles per hour at sea level, strange things happened. Controls became difficult to move. Wings shook violently. Some aircraft broke apart. Pilots called this the sound barrier, and many believed it was an absolute limit, that aircraft simply could not fly faster than sound. Aerodynamicists understood the problem. At supersonic speeds, air behaves differently, creating shockwaves that can destroy an aircraft. But on October 14, 1947, a young test pilot named Chuck Yeager climbed into an experimental rocket-powered aircraft called the Zone and was dropped from a bomber at high altitude. He fired the rocket engine and accelerated faster and faster until suddenly the buffeting stopped. The ride became smooth, and the instruments showed he was flying faster than sound. He had broken through the barrier. The sonic boom his aircraft created was heard on the ground below. What had seemed impossible was now achieved. Within years, supersonic flight became routine for military aircraft. The sound barrier was not a wall, but a threshold, one that courage and engineering together could cross. Chuck Yeager broke the sound barrier with 2 broken ribs. What makes Chuck Yeager's achievement even more remarkable is that he accomplished it while injured. 2 days before the record attempt, Yeager went horseback riding and was thrown from his horse, breaking 2 ribs. He did not report the injury because he knew the flight would be cancelled if anyone found out. On the morning of the test, he was in considerable pain and could not even close the hatch of the Zone aircraft by himself. He and a friend rigged up a piece of broomstick that he could use as a lever to seal the door. Then Yeager was dropped from the B-29 bomber carrying his aircraft, ignited the rocket engine, and pushed through the pain to make history. His matter-of-fact approach to an incredibly dangerous test flight, his refusal to let injury stop him, exemplified the spirit of test pilots in that era. They were military pilots, often combat veterans, volunteering to fly experimental aircraft, knowing that many of their colleagues had died in earlier tests. They were calm, professional, and extraordinarily brave. Jet engines are simpler than piston engines, with far fewer moving parts. It seems counterintuitive that something as powerful and sophisticated as a jet engine could be simpler than the engine in a car, but it is true. A piston engine has thousands of parts, hundreds of them moving, pistons pumping up and down, valves opening and closing, crankshafts spinning, all timed precisely. A jet engine, by contrast, has far fewer moving parts. Air is sucked in by a large fan, compressed by a series of spinning blades, mixed with fuel and ignited, then expelled out the back. The only major moving parts are the spinning blades on a central shaft. There are no pistons, no valves, no complicated timing mechanisms. This simplicity makes jet engines remarkably reliable. They can run for thousands of hours without major maintenance. They are powerful for their weight, efficient at high altitudes where the air is thin. The steady roar of a jet engine is actually a continuous controlled explosion, a sustained burn that creates smooth, reliable thrust. This elegant simplicity helped jets take over aviation so quickly. They were not just faster, they were more reliable and easier to maintain than the complex piston engines they replaced. The jet age brought luxurious travel to the skies in the 1950s. As jet aircraft entered commercial service in the late 1950s and early 1960s, flying transformed from adventure into luxury. Aircraft like the Boeing 707 and the Douglas DC-8 could carry over 100 passengers in spacious cabins. Airlines competed to offer the most elegant service, with gourmet meals served on china, complimentary champagne, and flight attendants in designer uniforms. The seats were wide and comfortable, with generous legroom. Passengers dressed formally for flights, men in suits, women in dresses and heels, treating air travel as a special occasion. Tickets were expensive, affordable only to the wealthy or business travelers on expense accounts. But for those who could afford it, flying was glamorous, an experience as memorable as the destination. Aircraft had lounges where passengers could socialize, sometimes even piano bars. The speed of jets made the world suddenly smaller. New York to Los Angeles took 5 hours instead of 12. London to New York, 7 hours instead of 18. The world was shrinking, and doing so in style. The age of widespread flight. The Boeing 747 brought wide-body jets to the world. In 1969, Boeing introduced an aircraft so large it seemed impossible. The 747, nicknamed the Jumbo Jet, had 2 aisles in its passenger cabin, could carry over 400 people, and featured an iconic hump on the upper deck that gave it an instantly recognizable profile. Airlines were skeptical at first. They worried it was too big, that they could never fill all those seats. But the 747 proved them wrong. It made international travel affordable for millions of people, carried cargo across oceans, and became the backbone of long-distance aviation for decades. The 747's size allowed airlines to offer lower fares while still making a profit. For the first time, ordinary people could afford to fly to other continents. The upper deck became famous for first-class luxury, with lounges and beds. The aircraft was also remarkably reliable, capable of flying transoceanic routes with just 2 pilots. The 747 changed what was possible in aviation, proving that bigger could indeed be better. Flying became affordable for ordinary people in the 1970s. As aviation matured, competition between airlines increased and costs came down. Air travel slowly became accessible to more people. In the 1970s, deregulation in the United States allowed new airlines to enter the market, competing on price. Budget carriers emerged, offering basic service at lower fares. Advances in technology made aircraft more efficient, burning less fuel per passenger. Larger aircraft spread costs across more seats. Gradually, flying transformed from luxury to utility, from special occasion to practical transportation. Families began taking vacations by air. Students flew home for holidays. Business travel expanded as companies sent more employees to meetings across the country. By the 1980s, millions of people were flying who had never been on an aircraft before. The democratization of flight fulfilled the early pioneers' dreams, making the sky accessible not just to the wealthy, but to everyone. Today, billions of passengers fly each year, treating it as casually as taking a bus. What was once magic has become mundane, yet no less miraculous for its ordinariness. The Concorde flew passengers faster than the speed of sound. While most commercial aviation focused on efficiency and capacity, one aircraft pursued pure speed. The Concorde, a joint British-French project, entered service in 1976 as the world's only supersonic passenger airliner. It could cruise at twice the speed of sound, reducing flight times dramatically. London to New York took just over 3 hours instead of 8. The aircraft was beautiful, with a slender fuselage and graceful delta wings. Flying on Concorde was an exclusive experience, with tickets costing many thousands of dollars. Passengers could watch the Mach meter as the aircraft accelerated through the sound barrier, could see the curvature of Earth through small windows, could arrive before they left in terms of time zones crossed. But the Concorde was never economically successful. It was expensive to operate, could carry only 100 passengers, and its sonic booms restricted where it could fly over land. After a tragic crash in 2000, and flights ended in 2003, today, no supersonic passenger aircraft fly. But the Concorde remains a symbol of aviation's ambition, of what is possible when speed matters more than cost. Modern airliners are incredibly fuel efficient. Today's commercial aircraft are engineering marvels of efficiency. A modern airliner can carry hundreds of passengers thousands of miles, while burning less fuel per person than most automobiles use. This efficiency comes from decades of refinement. Engines have become extraordinarily sophisticated, extracting maximum energy from every drop of fuel. Wings are shaped with computer-designed curves that reduce drag. Aircraft are built from advanced materials, carbon fiber composites, and aluminium alloys that provide strength with minimal weight. Even small details matter. Special paints reduce friction. Winglets, those small vertical fins at the wingtips, reduce vortices that waste energy. Airlines carefully calculate routes, altitudes, and speeds to minimize fuel consumption. The result is that modern aviation, despite moving millions of people daily, has a smaller environmental impact per passenger mile than many other forms of transportation. Engineers continue pushing for even greater efficiency, designing aircraft with even more advanced engines, lighter materials, and better aerodynamics. The goal is to make flight sustainable, to allow humanity's dream of air travel to continue, while protecting the planet that makes all dreams possible. Commercial aircraft can glide surprisingly far without engines. One of aviation's most reassuring facts is how well aircraft glide. If all engines fail, which is extraordinarily rare, a commercial airliner does not fall from the sky like a stone. It becomes a glider, able to descend slowly and controlledly toward a landing. A typical airliner at cruising altitude, about 35,000 feet, can glide roughly 100 miles before reaching the ground. Pilots train extensively for this scenario, practicing engine-out procedures in simulators. There have been real incidents where aircraft lost all engine power, yet landed safely. In 2001, an Air Transat flight ran out of fuel over the Atlantic, but glided to a safe landing in the Azores, traveling over 75 miles without power. In 2009, US Airways Flight 1549 lost both engines after hitting birds, but was glided safely onto the Hudson River in New York. These incidents, while terrifying for those aboard, demonstrate how well aircraft are designed and how skilled modern pilots are. The ability to glide provides a safety margin, time for pilots to solve problems or find a place to land, reassurance that even in worst-case scenarios, aircraft can be controlled. Pilots train for years before flying commercial aircraft. The person sitting in the cockpit of your flight has undergone extensive training, far more than you might realize. It begins with basic flight training, learning to fly small, single-engine aircraft, mastering takeoffs, landings, navigation, and emergency procedures. Then comes more advanced training in larger aircraft with more complex systems. Pilots must accumulate thousands of flight hours before airlines will hire them. Once hired, training continues. They learn the specific aircraft type they will fly, spending weeks in ground school studying systems. then more weeks in flight simulators practicing normal and emergency procedures. They train for scenarios they will hopefully never face: engines failing, fires, electrical problems, extreme weather. This training continues throughout their careers, with recurrent simulator sessions every few months. Pilots are also required to undergo regular medical examinations and proficiency checks. By the time a pilot is flying a modern airliner, they have likely spent 10,000 hours or more in aircraft, encountered countless situations, and been trained to handle nearly anything. This extensive preparation makes flying one of the safest forms of transportation. Autopilot systems help pilots, but never replace them. Modern aircraft have sophisticated autopilot systems that can fly the aircraft for much of the journey, following programmed routes, maintaining altitude and speed, even landing in poor weather. This might sound like pilots are unnecessary, but nothing could be further from the truth. Autopilots are tools that help pilots manage workload, allowing them to focus on monitoring systems, communicating with air traffic control, planning for contingencies, and making decisions. Pilots program the autopilot, telling it what to do. They monitor its performance, ready to take control instantly if anything unusual happens. The autopilot cannot handle unexpected situations, cannot make judgment calls, cannot adapt to circumstances outside its programming. In any emergency, pilots disconnect the autopilot and fly manually. Modern aviation works because of this partnership between human judgment and computer precision. Machines handle routine tasks with perfect consistency. Humans provide creativity, intuition, and the ability to handle the unexpected. Far from replacing pilots, automation has made their jobs more complex, requiring them to be systems managers, understanding not just how to fly, but how all the aircraft's computers work together. Air traffic control coordinates thousands of flights every day. In the sky above us, invisible highways crisscross in 3 dimensions. Aircraft follow these airways, guided by air traffic controllers who work in darkened rooms, staring at radar screens, talking calmly to pilots, ensuring aircraft stay safely separated. It is an extraordinarily complex dance. At any moment, thousands of aircraft are in flight, each moving at hundreds of miles per hour, each needing to depart, climb, cruise, descend, and land without interfering with others. Controllers assign altitudes, approve route changes, coordinate handoffs as aircraft move from one controller's airspace to another's. They manage the flow of traffic into busy airports, spacing arrivals so aircraft land at safe intervals. They watch for weather, rerouting flights around storms. They handle emergencies, clearing airspace for aircraft in trouble. It requires intense concentration, quick thinking, and calm professionalism. Yet it works remarkably well. Thousands of flights operate daily, with minimal delays and extraordinary safety. The system is a testament to human organization, to our ability to create complex systems that function smoothly, even under pressure. Aircraft are designed with multiple backup systems. Safety in aviation comes from redundancy. Every critical system on a modern airliner has backups, and those backups have backups. Engines are designed to fail safely, and aircraft can fly with one engine out. If the primary electrical system fails, backup generators activate. If those fail, batteries provide emergency power. Hydraulic systems, which move flight control surfaces, have multiple independent circuits. If one fails, others take over. Navigation systems have backups. Communication radios have backups. Even the flight controls themselves have redundancy, with cables or computers providing multiple paths for pilot commands to reach control surfaces. This redundancy means that single failures, or even multiple failures, rarely lead to disasters. Aircraft can continue flying safely even when things go wrong. Pilots joke that aviation is hours of boredom punctuated by moments of sheer terror. But the reality is that even the terrifying moments usually end safely because of all these backup systems. Designers assume things will fail and plan accordingly, building layers of protection into every aircraft. Lightning strikes aircraft regularly without causing harm. It might seem terrifying, but aircraft are struck by lightning quite frequently, on average once per aircraft per year. Yet these strikes rarely cause problems. Aircraft are designed to handle lightning safely. The aluminum, or composite structure, conducts the electricity harmlessly around the cabin and back out into the air. Passengers and crew inside are protected, sitting within what is essentially a Faraday cage. Pilots might see a flash, hear a loud bang, but the aircraft continues flying normally. After landing, maintenance crews inspect the aircraft to ensure no damage occurred, but usually they find only small scorch marks where the lightning entered and exited. Modern aircraft have protections built in. Fuel tanks are designed to prevent ignition. Electronic systems are shielded against electrical interference. Flight control cables are routed to avoid vulnerable areas. The result is that lightning, despite its awesome power, poses little threat to modern aircraft. It is just one more natural phenomenon that engineers have learned to manage, turning something potentially dangerous into a minor inconvenience. Airports never truly close, operating around the clock. At any hour of the day or night, somewhere, an aircraft is taking off or landing. Major airports operate continuously, with flights scheduled across all 24 hours. Ground crews work in shifts, fueling aircraft, loading luggage, catering meals, cleaning cabins. Air traffic controllers work through the night, guiding red-eye flights across continents. Even during the quietest hours, from 2 to 5 in the morning, cargo aircraft land and depart, carrying packages, mail, and freight. Maintenance crews use overnight hours when passenger traffic is lightest to service aircraft, fixing problems, performing inspections, preparing planes for the morning rush. The airport is a city that never sleeps, lit by thousands of lights, filled with motion and purpose. For travelers arriving on late-night flights or departing on early morning ones, there is something surreal about the experience. Walking through terminals when most of the world sleeps, watching aircraft taxi in darkness, seeing the dedication of workers who keep the system running while others dream. Runways are numbered based on their magnetic heading. If you have ever wondered what the numbers painted on runways mean, the answer is elegantly simple. They represent the magnetic heading of the runway, rounded to the nearest 10 degrees, and with the last digit dropped. A runway pointing due north at 360 degrees is labeled runway 36. A runway pointing east at 90 degrees is runway 09. Since runways can be used in either direction, they have two numbers, one for each end. The opposite end of runway 09, facing west at 270 degrees, would be runway 27. This system allows pilots to quickly orient themselves, ensuring they are approaching the correct runway from the correct direction. At night, in poor weather, when landmarks are invisible, these numbers become crucial navigation aids. The system is universal, used at airports worldwide, one of the many international standards that make global aviation possible. Every detail of flight operations has been carefully standardized, allowing pilots from any country to operate safely at any airport in the world. Taxiways are like roads connecting runways to terminals. The paved areas at airports are more complex than most passengers realize. Runways are where aircraft take off and land, but between runways and the terminal buildings is an intricate network of taxiways, paths that aircraft follow to get from one place to another. Each taxiway has a letter designation: Alpha, Bravo, Charlie, and pilots are given specific routes to follow. Ground controllers guide aircraft along these paths, much like dispatchers directing vehicles on roads. The taxiway system allows multiple aircraft to move simultaneously without interfering with each other. Some taxiways cross active runways, requiring careful coordination to ensure aircraft and vehicles cross safely between landing and departing flights. Painted lines, lights, and signs guide pilots, especially at night or in poor visibility. Large airports can have miles of taxiways, and it is easy for pilots unfamiliar with an airport to get lost. That is why ground controllers are constantly communicating, confirming positions, providing directions, ensuring everyone knows where they are and where they are going. This hidden infrastructure is essential to keeping airports flowing smoothly, moving hundreds of aircraft each day without chaos. Aircraft create vortices that trail behind them in flight. As an aircraft flies, its wings generate lift by creating a pressure difference between upper and lower surfaces. This pressure difference causes air to spiral off the wingtips in powerful rotating vortices, like horizontal tornadoes trailing behind the aircraft. These wake vortices are invisible, but can be dangerous. A smaller aircraft flying into the wake of a larger one can be flipped or thrown violently by the turbulence. This is why air traffic control enforces strict separation between aircraft, especially during takeoff and landing, when aircraft are slow and vulnerable. The size and strength of wake vortices depend on the aircraft's weight, so heavy aircraft like the 747 or a 380 generate particularly strong wakes. Controllers space aircraft farther apart when following large aircraft. The vortices gradually dissipate, sinking and spreading until they disappear. On humid days, you can sometimes see them as thin condensation trails spiraling off wingtips. They are a reminder that aircraft do not move through the air without leaving a trace, that they disturb and shape the air around them, invisible yet powerful. Contrails form when hot exhaust meets cold air. On a clear day, you might look up and see white lines streaking across the sky behind high-flying aircraft. These are contrails, short for condensation trails, and they form in a way similar to how you can see your breath on a cold day. Aircraft engines burn fuel and produce hot, moist exhaust. At high altitudes, where temperatures can reach 60 degrees below zero, this moisture instantly condenses and freezes into tiny ice crystals. These crystals form the white trail behind the aircraft. Where the contrails form depends on temperature and humidity. Sometimes aircraft fly without leaving any trail because conditions are not right. Other times, contrails persist for hours, spreading into thin cirrus clouds. Scientists study contrails because they can affect climate, reflecting sunlight and trapping heat in complex ways. To passengers below, they are beautiful, white chalk lines drawn across the blue canvas of the sky, temporary art created by the simple meeting of hot and cold, of human technology and natural atmosphere. You can see the curve of Earth from cruising altitude. At typical cruising altitude, around 35,000 feet, or about 7 miles up, passengers looking out the window can see the gentle curve of the horizon. It is subtle, not the dramatic arc visible from space, but unmistakably present. The Earth is indeed round, and from this height, you can see the proof with your own eyes. On clear days, you can see for hundreds of miles, watching landscapes stretch to the horizon in all directions. Mountains appear as wrinkles, cities as patterns of light and shadow, rivers as silver threads wandering through terrain. Cloud layers below look like vast cotton landscapes, extending to infinity. This view puts human activity in perspective. Borders invisible, conflicts remote. The planet appears as what it is, one world, beautiful and fragile, suspended in the black void of space. This perspective was once available only to astronauts. Now, millions experience it daily, though many travelers pull down the window shade, missing the profound gift of this elevated viewpoint. Those who look out understand why pilots love flying, why the view never grows old. Aircraft windows are small and round for important reasons. Airplane windows are much smaller than windows in buildings, and they have rounded corners rather than square ones. Both features are deliberate safety measures. In the early days of jet aviation, some aircraft had large square windows. As aircraft were pressurized and flew higher, these square windows created stress concentrations at the corners. Cracks would form and spread, sometimes catastrophically. The most famous example was the de Havilland Comet, the world's first jet airliner, which suffered several crashes due to metal fatigue around square windows. Engineers learned that round or oval windows distribute stress more evenly, making the fuselage stronger. Windows are small to minimize the area where the pressure difference between inside and outside the aircraft exists. Each window is a potential weak point, so keeping them small improves safety. Modern aircraft windows are actually made of multiple layers, typically 3 panes, each capable of holding pressure on its own. The tiny hole you sometimes see in the window is deliberate, allowing pressure to equalize between the panes and preventing fog. Every detail, no matter how small, serves a purpose in aviation. The air inside the cabin comes from the engines. At cruising altitude, the outside air is too thin to breathe and too cold to survive in, colder than Antarctica. So how do aircraft maintain breathable, comfortable air inside? The answer lies in the engines. As air enters the jet engine, some is compressed before reaching the combustion chamber. This compressed air, called bleed air, is tapped off before it mixes with fuel. It is still extremely hot, hundreds of degrees, so it passes through heat exchangers and cooling systems to bring it to a comfortable temperature. Then it is pumped into the cabin through overhead vents. The air circulates through the cabin and is eventually vented out through valves that control cabin pressure. Contrary to common belief, cabin air is not recirculated endlessly. About half is fresh from outside, half filtered and recirculated. The system maintains pressure equivalent to about 6,000 to 8,000 feet elevation, which is why your ears pop during climb and descent. This environmental control system is one of the most complex parts of the aircraft, constantly adjusting to maintain comfortable conditions as the aircraft climbs, descends, and flies through varying atmospheric conditions. Aircraft cabins are pressurized to allow comfortable high-altitude flight. Without pressurization, flying at high altitudes would be impossible for passengers. At 35,000 feet, the air pressure is only about 1/4 what it is at sea level, far too thin to breathe. Passengers would lose consciousness within seconds, suffer severe altitude sickness, possibly die. The solution is to pump air into the sealed cabin, maintaining pressure artificially. The cabin is like a balloon inflated against the low pressure outside. The pressure difference is substantial, about 8 pounds per square inch, which over the entire fuselage surface amounts to hundreds of thousands of pounds of force trying to expand the aircraft like a balloon. This is why the fuselage is cylindrical. That shape best resists internal pressure. It is also why aircraft have such thick, strong structures. Pressurization allows passengers to sit comfortably in shirt sleeves while flying through the icy thin air of the stratosphere. It is one of the key technologies that made high-altitude jet flight practical, allowing aircraft to fly above most weather, in smooth air, faster and more efficiently than lower-altitude flight would allow. The Boeing 787 windows can electronically dim instead of using shades. Modern aircraft incorporate remarkable innovations, and the Boeing 787 Dreamliner offers one particularly delightful example. Instead of traditional window shades that pull down mechanically, the 787 has electrochromic windows. Press a button, and the window gradually darkens, changing from clear to translucent to opaque blue. It uses an electric current to change the properties of a gel layer in the window, blocking light while still allowing passengers to see out, just more dimly. The system has several settings, so cabin crew can dim all windows partially during meal service or darken them completely for overnight flights, all controlled electronically. Passengers can still override the controls to see out if they want. This technology serves several purposes. It reduces glare and heat from sunlight, improving cabin comfort. It weighs less than traditional shades, saving fuel, and it simply looks futuristic, making the flying experience feel more modern. Small touches like this remind us that aviation continues to evolve, that each generation of aircraft brings new refinements, new ways to make flight more comfortable and efficient. Some aircraft can fly for over 20 hours non-stop. The longest commercial flights in the world are remarkable feats of endurance. Routes like Singapore to New York or Perth to London cover more than 9,000 miles and take over 19 hours in the air. These flights are made possible by modern ultra-long-range aircraft like the Airbus A350 and Boeing 777 variants, designed specifically for such journeys. They carry enormous amounts of fuel, so much that the aircraft is significantly heavier at takeoff than landing, burning off thousands of pounds per hour. The engines are remarkably efficient, sipping fuel carefully to make the reserves last. For passengers, these flights require patience. Airlines provide extra amenities, better meals, more entertainment options, trying to make nearly a full day in the air tolerable. For pilots, there are special crew rest requirements, usually 4 pilots working in shifts, so no one is in control for too long without rest. These flights eliminate layovers, getting passengers from A to B without intermediate stops, but they push both human and machine endurance to remarkable limits. They represent the cutting edge of what modern aviation can achieve. The Airbus A380 is the world's largest passenger airliner. If the Boeing 747 seemed impossibly large when it was introduced, the Airbus A380 took size to an entirely new level. This double-decker giant can carry over 800 passengers in high-density configurations, though airlines typically configure them for around 500 in mixed classes. The wingspan stretches almost 300 feet. The aircraft stands 8 stories tall. It is so large that airports had to modify their infrastructure, widening taxiways, reinforcing pavement, building special gates with bridges to both decks. Despite its size, the A380 is remarkably quiet and smooth to fly in. The cabin feels spacious, not cramped. The sheer mass absorbs turbulence effectively. Airlines configured them with bars, lounges, even showers for first-class passengers. Yet the A380 was not the commercial success Airbus hoped for. Airlines increasingly prefer smaller, more efficient twin-engine aircraft that can serve more routes with less risk. Production ended in 2021 after just over a decade. Still, the A380 remains a marvel, the largest passenger aircraft ever to fly regularly, a testament to what engineering can achieve when the goal is simply to build the biggest. The science and wonder of flight. Wings create lift through pressure differences above and below. The magic of flight comes down to a simple principle that feels almost too elegant to be true. As a wing moves through the air, its curved upper surface forces air to travel farther and faster than air flowing under the flatter lower surface. According to Bernoulli's principle, faster moving air creates lower pressure, so the pressure above the wing is lower than the pressure below, and this pressure difference pushes the wing upward. This upward force is lift, and it is what allows aircraft to overcome gravity and fly. The amount of lift depends on many factors: the wing's shape, its angle to the oncoming air, the speed of the aircraft, the density of the air. Pilots control lift by changing speed and adjusting the wing's angle of attack. At slow speeds, they need more angle to generate sufficient lift. At high speeds, less angle is needed. Understanding lift took humanity thousands of years, but once we grasped it, the sky opened to us. Every bird, every insect, every aircraft uses this same elegant principle, this dance of air and pressure that defeats gravity itself. Flaps extend from wings to increase lift at low speeds. If you watch an aircraft landing or taking off, you will notice panels extending from the trailing edge of the wings. These are flaps, movable surfaces that change the wing's shape and increase lift. At cruising speed, the wing is optimized for efficiency, slim and clean. But during takeoff and landing, the aircraft is moving slowly and needs more lift to stay airborne. Extending flaps increases both the wing's area and its curvature, allowing it to generate more lift at lower speeds. Different flap settings provide different amounts of lift and drag. Pilots select the appropriate flap setting for each phase of flight. After takeoff, as speed increases, flaps are gradually retracted. Before landing, they are extended again. There are several types of flap designs: simple hinged flaps, split flaps, slotted flaps that allow air to flow through gaps for extra lift. The engineering is sophisticated, but the goal is simple: to let the same wing work efficiently, both fast and slow, in cruise and during takeoff and landing. Slats on the wing's leading edge help prevent stalls. While flaps extend from the trailing edge of the wing, slats extend from the leading edge, the front. They serve a similar purpose: improving lift at low speeds, but work in a different way. When slats extend, they create a gap that allows high-pressure air from below the wing to flow over the top, energizing the airflow and helping it stay attached to the wing surface. This prevents the airflow from separating, which would cause a stall, a loss of lift. Slats allow the wing to operate at higher angles of attack without stalling. On many airliners, slats extend automatically with the flaps, controlled by the same lever. Pilots do not usually think about them separately, but they are crucial for safe, low-speed flight. Without slats, wings would need to be much larger, or aircraft would need to fly faster during takeoff and landing, requiring longer runways. These small, seemingly simple devices enable aircraft to operate from reasonably sized airports, making air travel practical and safe. The fuselage is shaped to minimize drag. The tube-shaped body of an aircraft, the fuselage, is not just a container for passengers and cargo. Its shape is carefully designed to slip through the air with minimum resistance. Drag, or air resistance, wastes fuel and limits speed. Engineers shape the fuselage to be streamlined, with a rounded nose that pushes air smoothly aside, a long cylindrical body that keeps airflow attached, and a tapered tail that allows air to close back together behind the aircraft. Every bump, antenna, or protrusion creates drag, so designers work to minimize them. Even rivets and panel joints are carefully managed. On modern aircraft, surfaces are extraordinarily smooth. Composite materials allow for seamless construction without the rivet lines of older aluminium aircraft. Wind tunnels and computer simulations test countless variations, seeking the perfect balance between interior space structural strength, and aerodynamic cleanliness. The result is that modern airliners slip through the sky efficiently, wasting as little energy as possible, fighting air resistance, allowing them to carry hundreds of passengers thousands of miles on reasonable amounts of fuel. The tail keeps the aircraft stable. At the back of every aircraft is the tail, technically called the empennage, and it serves crucial purposes. The vertical stabilizer, the tall fin standing upright, keeps the aircraft pointed in the right direction, preventing it from yawing side to side. The horizontal stabilizer, mounted near the tail, keeps the nose from pitching up or down. These surfaces work like the feathers on an arrow, providing stability. Without them, aircraft would tumble through the sky, impossible to control. The tail surfaces also carry control surfaces. The rudder, hinged to the vertical stabilizer, allows the pilot to yaw the nose left or right. The elevators, hinged to the horizontal stabilizer, control pitch, making the nose go up or down. On some modern aircraft, the entire horizontal stabilizer moves, rather than just the elevator. Pilots use these controls constantly, making tiny adjustments to keep the aircraft flying smoothly. The tail might seem like an afterthought, but it is as essential as the wings, the quiet partner that keeps everything stable and controllable. Ailerons control how the aircraft rolls. When an aircraft banks to turn, one wing rises and the other dips. This rolling motion is controlled by ailerons, hinged panels near the wingtips. They move in opposition. When the pilot moves the control stick or yoke to the left aileron goes up and the right aileron goes down. The upward aileron reduces lift on that wing, making it drop. The downward aileron increases lift, making that wing rise. The result is that the aircraft rolls in the direction the pilot commands. It is intuitive, almost like leaning into a turn on a bicycle. Once the aircraft is banked, the pilot uses the rudder to coordinate the turn, keeping it smooth and comfortable. Ailerons are surprisingly small, just a fraction of the wing's total area, but they are effective because they are far from the aircraft's center, giving them mechanical advantage. This elegant system of coordinated control surfaces, ailerons, elevator, and rudder, working together, gives pilots precise control over the aircraft's motion in 3 dimensions. Aircraft turn by banking, not by pointing the nose. It might seem that aircraft turn by pointing their nose in a new direction, like a car turning its wheels, but that is not how it works. In the air, there is no road to grip, no friction to push against. Instead, aircraft turn by banking, tilting one wing down and the other up. When the aircraft is banked, the lift generated by the wings is no longer pointing straight up, but is tilted. Part of that lift still supports the aircraft against gravity, but another part pulls it sideways, causing it to turn. The steeper the bank, the tighter the turn, but also the more lift is needed to maintain altitude. This is why turning aircraft often need to increase speed or angle of attack to generate that extra lift. Watching an aircraft bank gracefully into a turn, seeing the wings tilt and the nose swing around, is to witness a beautiful application of physics. The aircraft is not fighting the air but using it, working with nature's laws to accomplish something that seems impossible, changing direction while flying through a medium that offers no firm purchase. Turbulence is just air moving in different directions. For nervous flyers, turbulence can be unsettling, but it is simply air in motion, no different from waves on water. The atmosphere is a fluid, and like any fluid, it has currents, eddies, and waves. When an aircraft flies through these air currents moving in different directions, it bounces, sometimes gently, sometimes more severely. Turbulence can be caused by many things. Thermal turbulence occurs when the sun heats the ground unevenly, causing columns of warm air to rise. Mechanical turbulence is created when wind flows over mountains or buildings. Clear air turbulence, the most unpredictable kind, occurs at high altitudes where jet streams create invisible waves. For pilots, turbulence is a nuisance, making coffee spill and passengers nervous. But it is rarely dangerous. Modern aircraft are built to withstand far more stress than turbulence can deliver. Wings flex, absorbing the bumps. The structure is immensely strong. What feels dramatic to passengers is usually mild by engineering standards. Pilots often know when turbulence is coming and can avoid it or warn passengers. The seatbelt sign is not turned on because turbulence will damage the aircraft, but because it might toss unbuckled passengers around the cabin. Aircraft engines are tested by shooting frozen chickens into them. Aviation safety standards are remarkably thorough, and engine testing provides some of the most dramatic examples. Engines must prove they can withstand bird strikes, which are surprisingly common. To test this, engineers literally fire frozen chickens from a cannon into running engines at high speed. The engines must be able to sustain the impact, even ingesting the bird, and either continue running or shut down safely without shedding parts that could damage the aircraft. The tests are dramatic, with explosions of feathers and violent vibrations, but they ensure that when a real bird strike occurs, the engine can handle it. Engines are also tested in icing conditions, with water sprayed into them to create ice buildup, then blasted with heat to verify de-icing systems work. They are run continuously for hundreds of hours, pushed to maximum power, throttled back, throttled up again, simulating years of service in weeks. They are disassembled and inspected microscopically. Only after passing all these tests are engines certified for use. This exhaustive testing makes modern jet engines extraordinarily reliable, capable of running thousands of hours without failure. Jet engines can keep running even after ingesting birds or hail. Building on their robust testing, modern jet engines are remarkably resilient. A bird strike can be violent, with the bird entering the spinning blades at hundreds of miles per hour, but engines are designed to handle it. The fan blades are tough, made from titanium or advanced composites that can take impacts. If a blade does break, the engine casing is designed to contain it, preventing shrapnel from flying out and hitting the aircraft. Even after ingesting a bird, many engines can continue producing thrust, allowing the aircraft to fly safely to an airport. Similarly, hail can pepper the engine with ice balls, but it usually just passes through, melted by the engine's heat. Severe hail might reduce performance, but rarely causes complete failure. Volcanic ash is more serious because it can melt inside the hot engine and solidify coating components. But even then, engines can often be restarted after cooling. This resilience comes from decades of learning from incidents, analyzing failures, and building stronger, more tolerant systems. The engines hanging under airliner wings are triumphs of engineering, powerful yet remarkably robust. Reverse thrust helps slow aircraft after landing. When an airliner lands, you might hear the engines roar even louder than during takeoff. This is reverse thrust, a system that redirects engine power to help slow the aircraft. Jet engines normally push air backward, creating forward thrust. Reverse thrust systems deflect this airflow, sending it forward instead, creating a braking effect. On most jet engines, large clamshell doors or blocker panels move into position, redirecting the exhaust. The effect is dramatic, significantly shortening the landing roll. It is especially useful on wet or icy runways, where wheel brakes are less effective. The roar you hear is the engine at high power, with its exhaust being deflected forward and bouncing off the ground. Reverse thrust is not used to back up aircraft. though movies sometimes show this. It is only for slowing after landing. Once the aircraft has slowed to taxi speed, reverse thrust is cancelled, and the aircraft uses normal brakes and nose-wheel steering. This system is another example of making engines multifunctional, using the same powerful machinery for multiple purposes, efficient and elegant. Airplane tires are inflated to much higher pressures than car tires. The black rubber tires you see on aircraft landing gear look similar to car tires but are engineered to far higher standards. They are inflated to pressures of 200 pounds per square inch or more, compared to around 35 for a typical car tire. This high pressure is necessary because aircraft are extremely heavy. A fully loaded 747 weighs nearly 1 million pounds, and that weight is supported by just 18 main gear tires when on the ground. Each tire must carry tens of thousands of pounds. The high pressure allows the tires to support this weight without deforming excessively. Aircraft tires are also designed to withstand incredible abuse. They accelerate from 0 to over 150 miles per hour almost instantly when the aircraft lands. They must handle the heat generated by this friction, sometimes smoking from the friction of touchdown. They are made from special rubber compounds and reinforced with multiple layers of fabric and steel cords. Yet, despite their strength, they wear out relatively quickly and are regularly replaced. It is not unusual for airline tires to be changed after several dozen landings. Safety margins are generous, and worn tires are replaced long before they become dangerous. Landing gear is incredibly strong and sophisticated. The legs and wheels that support an aircraft on the ground are marvels of engineering. Landing gear must support the aircraft's entire weight, withstand the impact of landing, absorb the shock of touching down at high speed, and retract into the fuselage or wings to reduce drag during flight. The main gear, under the wings or fuselage, typically has multiple wheels that spread the load. The nose gear steers the aircraft on the ground. Each gear leg contains complex hydraulics, shock absorbers filled with oil and compressed gas that absorb landing impact, and mechanisms that allow the gear to fold and retract. The forces involved in landing are immense, sometimes several times the aircraft's weight concentrated in a split second. Yet landing gear handles these forces landing after landing, often for decades. When extended, gear locks mechanically, so even if hydraulic power is lost, the gear stays down safely. In emergencies, gravity alone can extend the gear, a simple backup that has saved aircraft when systems failed. The landing gear is hidden most of the time, retracted into the aircraft, but it is one of the most critical systems, the connection between the machine of the sky and the solid ground. Aircraft wings flex more than you might think. Looking out the window during a flight, you might notice the wings bending, flexing up and down as the aircraft encounters air currents. This can be alarming if you do not understand it, but wing flex is completely normal and designed in. Wings are not rigid beams. They are flexible structures that bend to absorb stress. During flight, wings generate lift, which pushes them upward. At the same time, the weight of the engines and fuel in the wings pulls them down. The result is constant flexing. During turbulence, wings can flex several feet up or down at the tips. This flexibility is a strength, not a weakness. Rigid wings would crack under stress. Flexible wings bend and return, absorbing energy. Before an aircraft is certified, wings are tested to destruction, bent upward until they break. They typically withstand forces far beyond anything they will experience in service, often bending so far the wingtips nearly touch above the fuselage before finally failing. This massive safety margin means that the flexing you see out the window is well within design limits, the wing doing exactly what it is supposed to do. Black boxes are actually bright orange. Aircraft carry flight data recorders and cockpit voice recorders. devices that record flight parameters and cockpit sounds throughout every flight. These are called black boxes, though they are actually painted bright orange to make them easier to find after an accident. They are incredibly tough, designed to survive crashes that destroy the rest of the aircraft. They can withstand enormous impacts, thousands of times the force of gravity, temperatures of over 1,000 degrees Celsius from post-crash fires, and immersion in deep ocean water for weeks. They contain memory chips that record the last hours of flight data and cockpit conversations. After an accident, investigators retrieve these boxes and analyze their data to understand what happened. The information they contain has led to countless safety improvements, identifying mechanical failures, procedural errors, and design flaws. Modern aircraft actually have multiple recording systems, with data uploaded via satellite in real time, so even if the physical recorders are never found, critical information is preserved. These orange boxes, small enough to hold in your hands, have made aviation safer by ensuring that every accident teaches lessons that prevent future ones. Modern aircraft are built from advanced composite materials. For most of aviation history, aircraft were built from aluminum, a metal that is light yet strong. But modern airliners increasingly use composite materials, primarily carbon fiber reinforced plastic. These composites are lighter than aluminum, do not corrode, and can be formed into complex shapes impossible with metal. The Boeing 787, for example, is about 50% composite by weight. The fuselage is made in large barrel sections, not thousands of pieces riveted together, but few large pieces bonded together. This reduces weight, improves strength, and eliminates thousands of potential failure points. Composites also allow for better cabin pressure and humidity, improving passenger comfort. The manufacturing process is different, more like sculpting than metalworking, with carbon fiber fabrics laid up in molds and then cured in enormous ovens called autoclaves. The result is an aircraft that is stronger, lighter, and more efficient than metal construction would allow. As technology improves, composites are becoming even more common, though aluminum is still widely used, especially for smaller aircraft. The future of aircraft construction is increasingly high-tech, with materials developed in laboratories replacing traditional metals. Manufacturing a single airliner takes months and thousands of workers. Building an aircraft is one of the most complex manufacturing tasks humans undertake. A modern airliner contains millions of parts, from enormous wing panels to tiny screws, sourced from suppliers around the world. Final assembly takes place in massive factories, buildings so large they create their own weather. The Boeing factory in Everett, Washington, is the largest building by volume in the world, big enough to assemble multiple 747s simultaneously. The Airbus factories in Europe are similarly enormous. Assembly is part choreography, part engineering. Fuselage sections are built separately, then joined. Wings arrive from other facilities and are carefully attached. Systems are installed, miles of wiring, hydraulic lines, air conditioning ducts. Engines are mounted. Everything is tested. Systems powered up. Thousands of checks performed. The aircraft is painted, a process requiring days and gallons of specialized paint. Finally, test flights ensure everything works. From the first parts being made to final delivery can take a year for a single aircraft. Thousands of engineers, technicians, and workers contribute. Each airliner is a masterpiece of organization and craftsmanship, a collaboration on an incredible scale. The human side of aviation. Flight attendants are trained in emergency procedures and first aid. The friendly faces serving drinks and meals are more than hospitality workers. Flight attendants undergo rigorous training, spending weeks learning safety procedures before ever working a flight. They learn how to evacuate an aircraft in 90 seconds, the certification standard for aircraft design. They practice opening emergency exits, deploying slides, and directing passengers in darkness and smoke. They learn to fight fires, administer first aid, and handle medical emergencies from heart attacks to childbirth. They train in water survival, how to deploy life rafts and help passengers in the ocean. They learn how to restrain violent passengers, handle hijacking situations, and deal with countless emergency scenarios. Recurrent training happens regularly throughout their careers. The cheerful professionalism they show while serving passengers conceals extensive safety training. In an emergency, they are the ones who will lead passengers to safety, calm panic, and save lives. Their primary job is not service, but safety, and they take that responsibility seriously. The next time a flight attendant demonstrates safety procedures, remember, they are showing you what might one day save your life. Pilots use checklists for everything, ensuring nothing is forgotten. Flying is complex, with hundreds of switches, systems, and procedures. To ensure nothing is missed, pilots use checklists for every phase of flight. Before starting engines, there is a checklist. Before taxiing, before takeoff, climbing, cruising, descending, landing, after landing, all have checklists. These are not suggestions, but required procedures. One pilot reads the item, the other pilot performs the action and confirms it is complete. This discipline prevents errors. Forgetting to lower landing gear, misconfiguring flaps, leaving a vital system off. These mistakes have caused accidents in the past. Checklists prevent them now. The discipline was borrowed from aviation by medicine, where surgical checklists have saved countless lives. Aviation pioneered the idea that even experts need reminders, that human memory is fallible, especially under stress. Emergency checklists help pilots handle failures systematically, working through problems step by step, rather than reacting impulsively. This culture of checklists is one reason aviation is so safe. Nothing is left to memory. Every critical action is verified, confirmed, checked. It is tedious, perhaps, but tedious is safe, and safe gets everyone home. Aircraft are meticulously inspected before every flight. Before passengers board, before engines start, aircraft undergo inspection. Pilots walk around the aircraft, looking for anything unusual, damage to the fuselage, leaks, worn tires, anything out of place. They check that control surfaces move properly, that panels are secured, that engines look normal. Inside, they review maintenance logs, confirming that any problems from previous flights have been fixed. They test systems, lights, radios, instruments, ensuring everything works. This pre-flight inspection catches problems before they become emergencies. Additionally, aircraft undergo deeper inspections at regular intervals. After a certain number of flight hours or days, mechanics inspect systems more thoroughly. Periodically, aircraft undergo major overhauls, where they are essentially taken apart, inspected piece by piece, and reassembled. These inspections follow strict regulations, with every item documented. Regulatory agencies audit airlines to ensure compliance. This layered approach, daily checks plus regular maintenance plus periodic overhauls, means that problems are caught early and fixed before they compromise safety. The aircraft you board has been looked over by multiple professionals who stake their reputations on its airworthiness. No two flights are exactly alike. Though airlines fly the same routes daily, every flight is unique. Weather varies, winds change, air traffic is different. Each flight requires adaptation. Pilots file flight plans before departure, specifying their route, altitude, and estimated times. But reality rarely matches plans perfectly. Air traffic control might assign different altitudes to separate traffic. Weather might require routing around storms. Winds might be stronger or weaker than forecast, affecting fuel consumption and arrival times. Pilots constantly monitor conditions, adjusting speed, altitude, route as needed. They communicate with controllers, with their airline's operations center, with other pilots sharing information. This flexibility, this constant small adaptation, is part of what makes aviation safe. Rigid adherence to a plan when conditions change would be dangerous. Instead, pilots make countless small decisions every flight, using their training and judgment to adapt to whatever the day brings. For passengers, the flight might seem routine, but in the cockpit, each flight is a unique challenge, familiar yet different, routine yet requiring constant attention. Flying is statistically far safer than driving. It is one of the most repeated statistics in aviation, yet it bears repeating because it is so profoundly true. Flying on a commercial airliner is extraordinarily safe, far safer than nearly any other activity. You are far more likely to be hurt driving to the airport than during the flight itself. In recent years, airlines in the United States and Europe have operated millions of flights with 0 passenger fatalities. Worldwide, fatal accidents are rare, often involving smaller airlines in less developed regions. The safety record is astonishing when you consider the complexity involved. Hundreds of people in a metal tube, miles above the earth, traveling at hundreds of miles per hour, yet it works. Flight after flight, day after day. This safety comes from everything we have discussed: rigorous training, redundant systems, careful maintenance, detailed procedures, lessons learned from past accidents. Aviation learns from every mistake, implements changes to prevent recurrence. The result is a transportation system that has become safer even as it has grown immensely. Billions of passengers fly each year, almost all arriving safely. The fear of flying is understandable, primal even, but the statistics are clear. You are safer in the air than on the road. The aviation industry learns from every accident. When accidents do occur, the response is thorough and systematic. Investigators from multiple agencies converge on the site. They document everything, photograph wreckage, interview witnesses, recover recorders, analyze data. The goal is not blame but understanding. What happened? Why did it happen? How can we prevent it from happening again? Investigations can take years, producing detailed reports hundreds of pages long. Recommendations are issued, and remarkably, they are usually implemented. If an accident reveals a design flaw, manufacturers fix it, not just on the crashed aircraft, but across the entire fleet worldwide. If it reveals a training gap, airlines update their programs. Regulatory agencies issue new rules. This process has been ongoing for over a century, each accident adding to aviation's collective knowledge. Modern aircraft and procedures reflect lessons learned from every tragedy. The industry does not hide mistakes or blame individuals. It treats accidents as learning opportunities, chances to improve. This culture of continuous improvement, of treating safety as a goal that is never fully achieved but always pursued, is why aviation keeps getting safer, decade after decade. Weather can delay flights but rarely prevents them. Passengers often complain about weather delays, but they reflect aviation's conservative approach to safety. Commercial aircraft can fly in remarkably bad weather. Rain, snow, even moderate ice are manageable. Modern aircraft have sophisticated weather radar, showing pilots exactly where storms are. They can deviate around severe weather or request different altitudes to find smoother air. But there are limits. Thunderstorms with severe turbulence and lightning are avoided. Heavy ice accumulation can affect performance. Extremely low visibility can make landing impossible. if the airport lacks sophisticated instrument landing systems. Crosswinds that are too strong can make landing unsafe. In these cases, flights are delayed until conditions improve or diverted to alternate airports. Pilots and airlines err on the side of caution. A delay is inconvenient. An accident is tragic. So flights wait, passengers grow frustrated, but everyone arrives safely. Modern forecasting helps, allowing airlines to anticipate weather and adjust schedules proactively. Still, weather remains one of the few factors beyond complete control, a reminder that for all our technology, nature still sets boundaries we must respect. Aircraft carry extra fuel for contingencies. When an aircraft departs, it carries more fuel than the minimum needed to reach its destination. Regulations require it. There must be enough fuel to reach the destination, plus divert to an alternate airport if the destination weather is poor, plus fly a holding pattern for a specified time, plus a reserve. This ensures that even if things do not go as planned, the aircraft has fuel to cope. Pilots monitor fuel carefully throughout the flight, knowing exactly how much they have versus how much they need. If they encounter strong headwinds or must divert around weather, burning more fuel than planned, they recalculate and may decide to land early to refuel. Running out of fuel is one of the few truly unforgivable errors in aviation, as it is almost always preventable with proper planning and judgment. The few accidents caused by fuel exhaustion are studied intensely, usually revealing a chain of poor decisions. Carrying extra fuel costs money, as fuel is heavy, and hauling extra weight burns more fuel. But it is non-negotiable. Safety margins are built into every flight. Oxygen masks drop automatically if cabin pressure is lost. At cruising altitude, the air is too thin to breathe. If the cabin loses pressure, whether due to a structural failure or a door opening, passengers would lose consciousness within seconds. To prevent this, aircraft have emergency oxygen systems. Above each seat, a compartment contains an oxygen mask connected to a chemical oxygen generator. If cabin pressure drops below a certain level, these compartments open automatically and masks drop down. Pulling the mask toward you activates the generator, which produces oxygen through a chemical reaction for about 12 to 15 minutes. This is enough time for the pilots, wearing their own oxygen masks, to descend to a lower altitude where the air is breathable. The safety briefing before every flight demonstrates how to use these masks, yet many passengers ignore it. In a real emergency, knowing how to quickly secure your mask could save your life. The instruction to secure your own mask before helping others makes sense. You cannot help anyone if you are unconscious. These simple yellow masks, often joked about, are a crucial last line of defense, ensuring passengers can breathe until the aircraft reaches safe altitude. In-flight medical emergencies are more common than you might think. Gather several hundred people in one place for several hours, and statistically, someone may have a medical issue. Heart attacks, strokes, seizures, allergic reactions, diabetic episodes, even women going into labor, all have happened aboard aircraft. When a medical emergency occurs, flight attendants ask if there is a doctor or medical professional aboard. Often there is, and they provide care using the aircraft's medical kit, which contains more than just band-aids. There are medications, diagnostic equipment, even automated defibrillators. For serious emergencies, the aircraft can communicate with ground-based medical professionals who provide advice. The decision whether to divert to the nearest airport or continue to the destination depends on the severity and the resources available. Diversions are not taken lightly, as they are expensive and disruptive, but they happen regularly, thousands of times per year worldwide. Some aircraft on very long routes carry enhanced medical equipment, essentially small flying clinics. Despite these emergencies, outcomes are usually good. The care provided, while basic, buys time until the patient can reach a hospital. Pilots eat different meals to prevent food poisoning. On international flights with multiple pilots, a little-known safety rule applies. The pilots eat different meals. This is not because of personal preference, but as a safety measure. If one meal is contaminated and causes food poisoning, only pilots who ate that meal will get sick. At least one pilot will remain healthy and able to fly the aircraft. This precaution might seem paranoid, but it reflects aviation's deep safety culture. Even unlikely risks are mitigated. Food poisoning has grounded pilots before, though rarely both pilots on the same flight. The rule is simple, effective, and costs nothing to implement. It is one of thousands of small details, most unknown to passengers, that collectively make flying safe. For passengers, food safety is also taken seriously. Airline caterers follow strict hygiene standards, with food prepared in specialized facilities and loaded onto aircraft in temperature-controlled containers. Meals are served at specific times to minimize the period they spend in the temperature danger zone. While airline food has a reputation for being unexciting, it is generally safe, prepared under standards stricter than many restaurants. The sound of landing gear retracting is normal and expected. Shortly after takeoff, passengers hear a loud mechanical thump and feel a vibration. This is the landing gear retracting into the fuselage or wings. It is a perfectly normal sound, though it can startle nervous flyers. Similarly, before landing, there is a thump as the gear extends and locks into place. These sounds are the aircraft reconfiguring itself, changing from flight mode to ground mode, or vice versa. Other sounds during flight are also normal. The hum of the air conditioning system, the whir of flaps extending, the roar of engines increasing power for climb. Flight attendants are trained to recognize normal sounds, and they remain calm because they know what each sound represents. If you are nervous about a sound during flight, watch the flight attendants. If they continue serving drinks and chatting calmly, whatever sound you heard is routine. They are your barometer for whether something is normal. Their calm professionalism reflects years of experience and training. They have heard it all before, thousands of times. If they are not concerned, you should not be either. Modern aircraft can land themselves in very low visibility. When fog blankets an airport, reducing visibility to near zero, flights still land safely. This is possible because of instrument landing systems, or ILS, and auto-land capabilities. The ILS uses radio beams to create an invisible path from the sky to the runway. The aircraft's computers follow this path with incredible precision, adjusting flight controls to stay on course. In the lowest visibility conditions, Category 3 approaches, aircraft can land with visibility so poor that pilots cannot see the runway until the aircraft has touched down. The autopilot flies the entire approach and landing, with pilots monitoring but not manually controlling the aircraft. Afterward, the autopilot even steers the aircraft along the centerline as it slows, until visibility improves enough for pilots to take over and taxi to the gate. This technology has made fog delays much less common. Decades ago, fog closed airports for hours or days. Now, appropriately equipped aircraft can land safely even when humans cannot see. It is another example of automation and human skill working together, machines providing precision, humans providing oversight and decision-making. Aircraft are designed to handle lightning strikes safely. As mentioned earlier, lightning strikes are common, but how are aircraft designed to handle them? The key is that the metal or composite structure of the aircraft creates a Faraday cage effect. The electrical charge from the lightning flows around the outside of the aircraft, from the entry point, usually a wingtip or nose, to an exit point, often the tail, without entering the cabin or damaging critical systems. Fuel tanks are designed so lightning cannot ignite fuel vapors. Wiring and electronic systems are shielded and grounded. After a lightning strike, the aircraft is inspected for entry and exit burn marks, but usually no damage is found beyond superficial scorching of the paint. Modern composite aircraft presented a challenge since carbon fiber conducts electricity differently than aluminum. Engineers developed special lightning protection systems, including metal mesh embedded in composite structures to safely conduct electricity. The result is that composite aircraft are just as safe in lightning as metal ones. Passengers inside the aircraft are protected, sitting within a conductive shell that directs electricity around them. It is similar to being safe inside a car during a lightning storm. The metal body protects you. The cruising altitude is chosen for efficiency and comfort. Airliners typically cruise between 30,000 and 43,000 feet. But why this range? The answer involves several factors. At these altitudes, the air is much thinner, producing less drag. This allows aircraft to fly faster using less fuel, dramatically improving efficiency. Jet engines also operate more efficiently in thin air, extracting more thrust from each gallon of fuel. Additionally, this altitude band is above most weather. Thunderstorms rarely reach above 40,000 feet, so cruise flight is usually smooth. The jet stream, high-altitude winds that can exceed 200 miles per hour, often flows in this altitude range. Airlines plan routes to ride tailwinds and avoid headwinds, sometimes changing altitude during flight to find the most favorable winds. However, there are limits. Too high, and the air becomes so thin that wings cannot generate enough lift, and engines struggle to produce thrust. The ceiling varies by aircraft and weight. Heavier aircraft, with more passengers and fuel, fly lower. As fuel burns off, they can climb to more efficient altitudes, a process called step climbing, the global network. Airlines coordinate complex networks spanning the globe. Flying from one city to another seems simple from a passenger's perspective, but behind it is an intricate global system. Airlines operate hub-and-spoke networks, with major airports serving as hubs where passengers connect between flights. A passenger might fly from a small city to a hub, then connect to another flight to their final destination. This system allows airlines to serve many city pairs efficiently without flying direct between every possible combination of cities. Scheduling is complex, optimizing aircraft utilization, crew schedules, gate availability, and passenger connections. Aircraft must be maintained, positioned for the next day's flights, and used as efficiently as possible since they are expensive assets. Crews must be scheduled following strict rest requirements, with reserve crews available for irregularities. When weather or mechanical issues disrupt the schedule, operation centers work frantically to recover, rerouting aircraft and crews, rebooking passengers, sometimes chartering additional aircraft. Coordinating thousands of daily flights, involving hundreds of aircraft and tens of thousands of crew members, is one of the most complex logistics problems in existence. Yet it mostly works, a testament to planning, technology, and the dedication of countless people behind the scenes. Flight attendants may work for many airlines during their careers. Being a flight attendant was once considered a glamorous career, and it remains rewarding but challenging. Attendants work irregular schedules, often away from home for days at a time, sleeping in hotels between flights. They are on their feet for hours, dealing with passengers, some delightful, some difficult. The job requires patience, physical stamina, and adaptability, yet many attendants love it enjoying the travel, the variety, the camaraderie with crew members. It is not unusual for attendants to work for multiple airlines during their careers, starting with regional carriers, moving to major airlines, sometimes switching airlines for better routes or bases closer to home. Senior attendants bid for desirable routes, international flights to interesting destinations, while junior attendants work less desirable schedules. Despite challenges, there is a strong culture and sense of community. Flight attendants often form lifelong friendships with crew members, sharing unique experiences that ground-based workers never encounter. They have seen the world from a perspective few others experience, and that shapes them. Some pilots fly cargo at night, while others fly passengers by day. Not all pilots fly passenger aircraft. Cargo airlines operate extensive networks, moving goods around the world. These flights happen mostly at night, when passenger traffic is lower and airports have capacity. Cargo pilots fly the same aircraft types as passenger pilots, often 747s, 767s, or wide-body aircraft. But instead of passengers, they carry everything from electronics to fresh flowers, medical supplies to auto parts. The lifestyle is different. Many cargo operations are overnight, with pilots flying while most people sleep, then resting during the day. There are no passengers to manage, no service, just the crew and their cargo. Some pilots prefer this, enjoying the quieter work environment. Others start in cargo and move to passenger airlines, or vice versa. The skills are similar, but the culture differs. Both passenger and cargo pilots are professionals, highly trained, but their daily experiences are quite different. Together, they keep the world moving, passengers by day, freight by night, the skies never quiet. Aircraft noise has decreased dramatically over the decades. If you lived near an airport in the 1960s or 70s, the noise was overwhelming. Early jet engines were extremely loud, their screaming roar audible for miles. Communities complained, leading to noise restrictions and curfews. Engineers responded by designing quieter engines. Modern turbofan engines, which use large fans to move more air more slowly, rather than expelling small amounts of air very fast, are much quieter. Aircraft also fly steeper approach and departure profiles, climbing quickly after takeoff to move away from populated areas, descending steeply to minimize time at low altitude. Airports have invested in noise barriers and insulation programs for nearby homes. The result is that modern aircraft are a fraction as loud as their predecessors. A modern 737 is dramatically quieter than the early 737s of the 1960s. Further improvements continue, with engineers testing even quieter engine designs and airframe modifications to reduce noise. The goal is to allow aviation to grow without increasing noise impacts on communities. It is a challenge, balancing the benefits of air travel against quality of life for those living near airports. But progress has been remarkable. The future of aviation includes electric and hybrid aircraft. Aviation faces a challenge, reducing its environmental impact. While modern aircraft are efficient, they still burn fossil fuels and produce emissions. The industry is exploring alternatives. Electric aircraft are already flying, mostly small trainers and experimental aircraft. Batteries are heavy, limiting range, but technology is improving. Hybrid designs, combining electric motors with traditional engines, could extend range while reducing fuel consumption. For short routes, regional flights of a few hundred miles, electric or hybrid aircraft could become viable within decades. For long-haul flights, the challenge is greater. Batteries capable of powering a transatlantic flight would be impossibly heavy with current technology. Alternative fuels, sustainable aviation fuel made from renewable sources, offer another path. burning cleaner than petroleum-based jet fuel. Hydrogen is also being explored, either burned in engines or used in fuel cells. The transition will take time, but aviation is committed to reducing its environmental footprint. The dream of flight need not come at the cost of the planet. Future generations may fly in aircraft that are not only safe and efficient, but also sustainable. Supersonic flight may return for passengers. Though the Concorde retired, interest in supersonic travel has not disappeared. Several companies are developing new supersonic business jets and airliners. These designs aim to solve the problems that doomed Concorde, making supersonic flight economically viable and environmentally acceptable. One major challenge is the sonic boom, which restricted Concorde to overwater routes. New designs aim to reduce the boom to a gentle rumble, potentially allowing supersonic flight over land. Another challenge is fuel consumption. Supersonic flight burns more fuel per mile, but modern engine technology and aerodynamics can improve efficiency. If these challenges can be solved, supersonic travel could return, reducing long-haul flight times dramatically. New York to London in 3 hours instead of 7, Los Angeles to Tokyo in 5 hours instead of 11. For business travelers, this time, savings is valuable. Whether it will happen remains uncertain, but engineers are working on it. The allure of speed has not faded. Humans still dream of going faster, conquering distance, making the world smaller still. Some military aircraft can fly at over 3 times the speed of sound. While commercial aviation focuses on efficiency and capacity, military aviation pushes the boundaries of speed and maneuverability. Fighter jets, like the F-15 and F-16, can reach speeds over Mach 2, twice the speed of sound. The legendary SR-71 Blackbird reconnaissance aircraft could cruise at Mach 3.2, over 2,000 miles per hour, so fast that its titanium skin heated to over 500 degrees Fahrenheit from air friction. At that speed, it could cross the continental United States in just over an hour. These aircraft represent the pinnacle of aeronautical engineering, designed for missions where speed means survival. Their development pushed material science, aerodynamics, and engine technology forward, innovations that eventually filtered into commercial aviation. Today, military aircraft are exploring hypersonic speeds, faster than Mach 5, where traditional aerodynamics break down and physics becomes even more challenging. These extreme aircraft may seem distant from the commercial flights most people take, but they share the same basic principles of flight, and advances in one realm often benefit the other. Drones are reshaping aviation in unexpected ways. Unmanned aircraft, or drones, have exploded in popularity. From tiny consumer quadcopters to large military reconnaissance aircraft, drones are everywhere. They deliver packages, inspect infrastructure, film movies, survey crops, and much more. They operate without pilots aboard, controlled remotely or flying autonomously using GPS and computers. This raises new challenges. How do you integrate drones into airspace shared with manned aircraft? Collisions are a real risk. Regulations are evolving, requiring drone registration, restricting where they can fly, requiring operators to maintain visual contact or use electronic tracking. Some drones are nearly as large as traditional aircraft, capable of flying for hours at high altitudes. Others are small enough to fit in a backpack. The technology is advancing rapidly, with companies testing drone delivery systems that could eventually bring packages to your door by air. For aviation, drones represent both opportunity and challenge, a new dimension that must be safely integrated into a system built for manned flight. The skies are becoming busier and more diverse than ever before. Aviation connects families across continents. One of aviation's most profound impacts is social. Before affordable air travel, Emigrating to another country often meant never seeing your family again. Letters took weeks. Phone calls were expensive. Today, families separated by oceans can reunite for holidays or emergencies. Grandparents can meet grandchildren born halfway around the world. Students can study abroad, confident they can fly home if needed. This connectivity has reshaped human relationships, allowing families to spread across the globe while maintaining bonds. It has also enabled global business, with executives flying to meetings on other continents and returning the same week. Cultural exchange has flourished, with tourists experiencing foreign cultures firsthand. Aviation has made the world smaller, not in physical distance but in practical accessibility. The emotional impact of this connectivity is immeasurable. How many tearful reunions have happened in airport arrival halls? How many families stay together despite distance because of aviation? The industry measures success in passengers carried and flights completed, but its true measure might be in relationships maintained and experiences shared across distances that once seemed insurmountable. Airports are cities unto themselves. Modern airports are massive complexes, some larger than small towns. They contain everything a city needs: restaurants, shops, hotels, medical clinics, police and fire departments, power plants, fuel farms, maintenance facilities. The largest airports employ tens of thousands of people, from baggage handlers to air traffic controllers, janitors to airline executives. They operate their own transit systems, moving passengers between terminals. They have warehouses for cargo, secure areas for diplomats, customs and immigration facilities, chapels, museums, even art galleries. Some airports have conference centers and business facilities, allowing travelers to work between flights. The logistics of running an airport are staggering. Fresh water must be supplied, waste removed, electricity generated, roads maintained. Food must be delivered to dozens of restaurants and airline catering facilities. Jet fuel must be stored and delivered to aircraft. The coordination required is immense, involving hundreds of companies and government agencies. Yet airports mostly function smoothly, invisible machinery working behind the scenes to enable the visible miracle of flight. Some airports are built on man-made islands. When cities need airport capacity but lack land, they sometimes build airports offshore. Kansai International Airport in Japan and Hong Kong International Airport are both built on man-made islands constructed specifically for aviation. Engineers dumped millions of tons of rock and earth into the sea, creating islands large enough for runways, terminals, and all the infrastructure an airport needs. These projects cost billions and took years to complete. They solved critical problems, providing noise relief for nearby communities as aircraft take off and land over water, and creating space for expansion impossible on crowded mainlands. However, they face unique challenges. Islands must be protected from storms and rising seas. Runways require constant maintenance as the ground beneath settles. Access is by bridges or tunnels, creating potential bottlenecks. Despite challenges, these airports work well, serving millions of passengers annually. They represent human determination to overcome obstacles, bending geography itself to serve the needs of aviation. The highest airport in the world is over 18,000 feet elevation. Most airports are at or near sea level, but some serve communities in high mountains. Daocheng Yading Airport in China sits at an elevation of over 14,000 feet, and Kamdo Bamda Airport is even higher. At these elevations, the air is thin, creating challenges. Aircraft need longer runways to generate sufficient lift for takeoff and landing. Engines produce less power. Passengers and crew may experience altitude sickness. Special procedures are required. Yet these airports are lifelines for remote communities, providing connections that would otherwise require days of difficult mountain travel. Pilots who fly into high-altitude airports undergo special training, learning to manage the unique challenges. Passenger aircraft are pressurized, so once airborne, passengers do not experience the altitude, but on the ground, the thin air is noticeable. These extreme airports showcase aviation's adaptability, its ability to serve nearly any location, no matter how challenging. Some runways are built on reclaimed land extending into the ocean. Space constraints have led to creative solutions. Several airports have runways extending out into the sea, built on reclaimed land. Nice Côte d'Azur Airport in France and Gibraltar Airport, which actually crosses a public road, are examples. Construction involves building seawalls, filling the enclosed area with earth or rock, and compacting it to support runways. The advantage is that aircraft approach and depart over water, reducing noise for residents and avoiding terrain obstacles. The disadvantages include high construction and maintenance costs, vulnerability to storms, and environmental concerns about disturbing marine habitats. Despite challenges, these runway extensions have allowed airports to expand when landlocked by development. Each solution is unique, engineered for local conditions. Aviation adapts to geography, finding ways to build infrastructure where needed, sometimes quite literally creating new land to accommodate the growing demand for air travel. Airports use sophisticated radar systems to track aircraft. In the tower, controllers watch radar screens showing every aircraft in their airspace. Primary radar sends out radio waves and listens for reflections. Detecting aircraft like a bat uses sonar. Secondary radar queries aircraft transponders, receiving detailed information: the flight number, altitude, speed, identification. This allows controllers to see exactly where each aircraft is and where it is going. Modern systems display this information clearly, with data tags showing flight details. Controllers can see potential conflicts developing and take action to maintain separation. The system updates several times per second, providing real-time information. Beyond the airport, en route, controllers use similar systems to manage aircraft crossing the country or ocean. Aircraft also carry collision avoidance systems that communicate directly with each other, providing backup if controllers miss a potential conflict. Layers of technology, each backing up the others, work together to keep aircraft safely separated. Human controllers remain central, using their training and judgment to manage the system. But technology provides the information they need to make decisions quickly and accurately. Aircraft can communicate with the ground from anywhere in the world. Modern aircraft are never truly out of touch. Over land, they use VHF radios to communicate with air traffic control, the same technology as FM radio. Over oceans, beyond the range of ground stations, they use satellite communications, allowing pilots to send and receive messages, report positions, and receive clearances. Aircraft also transmit their position automatically using systems like ADS-B, which broadcasts GPS location, so anyone with a receiver can track them. Websites and apps allow people to watch aircraft movements in real time, seeing the path of every flight worldwide. This connectivity improves safety, allowing controllers to monitor aircraft even over remote oceans. But it also means pilots can receive updated weather information, communicate with their airline, and even allow passengers to send texts or emails in flight. The days of aircraft disappearing into silence between takeoff and landing are gone. Modern aircraft are connected, part of a global information network that enhances safety and efficiency, the joy and wonder of flight. There is something magical about watching an aircraft take off. Stand at the end of a runway, and the experience is visceral. You hear the engines power up, a deep roar that you feel in your chest. The aircraft begins to roll, slowly at first, then faster, accelerating down the runway. It seems impossible that something so large and heavy could lift into the air, yet it does. The nose rises, the wheels leave the ground, and suddenly the aircraft is flying, climbing smoothly into the sky. The landing gear retracts. The aircraft banks slightly, climbing higher and higher until it is just a speck, then gone. It happens dozens of times a day at every airport, yet it never stops being remarkable. Every takeoff is a small miracle, a triumph of engineering and human ingenuity. To watch it is to witness something that should not be possible. Heavy machines defying gravity through nothing more than cleverly shaped wings and powerful engines. It inspires wonder, reminding us what humans can achieve when we refuse to accept limitations. The view from a window seat is a gift. Passengers often request aisle seats for convenience, but window seats offer something special: the view. Watching the world shrink below as you climb, seeing the patchwork of fields, the threads of roads, the glittering ribbons of rivers, flying over mountains, their peaks sometimes below you, dusted with snow, crossing oceans, endless blue stretching to every horizon. Watching sunrises from above the clouds, the sky painted in shades of orange and pink, seeing cities at night, constellations of lights below mirroring stars above. This perspective is one that was unimaginable to most humans throughout history, reserved for birds and dreams. Now it is available on any flight for the price of a ticket. Yet many passengers ignore it, pulling shades closed, watching movies or sleeping. They miss the profound beauty outside, the constantly changing view of our planet from a perspective that is both humbling and uplifting. If you have the chance, choose a window seat sometimes. Look out, see the world as few generations before us could. Sunrises and sunsets look different from altitude. At cruising altitude, you are above much of the atmosphere, above the haze and pollution that filters light at ground level. Sunrises and sunsets are more vivid, colors more saturated. The sun seems to move faster, rising or setting in minutes, rather than the leisurely pace seen from the ground. You can sometimes see the shadow of the Earth on the horizon, a dark band separating sky from space. During sunset, this shadow rises from the east as the sun sinks in the west, the demarcation between day and night made visible. Sometimes you see the green flash, a rare optical phenomenon where the sun's last ray appears bright green for a split second. Pilots who fly regularly become connoisseurs of these aerial sunsets, seeing them in conditions impossible from ground. Each one is unique, painted by atmospheric conditions, clouds, and the angle of sunlight. For passengers paying attention, an in-flight sunset can be one of the most beautiful things they ever see. A natural light show performed at 40,000 feet. Flying through clouds is like entering another world. When an aircraft climbs through a cloud layer, the world outside the window transforms. Bright blue sky becomes gray or white mist. Visibility drops to nothing. The ground disappears. Sometimes clouds are thin wisps, quickly passed. Other times they are thick layers, thousands of feet deep, the aircraft flying blind through them for minutes. Then, suddenly, you break through the top, and the view is astonishing. Above the clouds, the sky is always clear, always blue, the sun always shining. Below is a white landscape of cloud tops, hills and valleys, and mountains of vapor, stretching to the horizon. It looks solid enough to walk on, though you know it is just water droplets. Flying above clouds is serene, peaceful, removed from earthly concerns. The weather below may be stormy, but up here, it is calm and bright. It is a reminder that perspective changes everything, that above the troubles and storms, there is always clear sky, always sunlight, if you climb high enough. Some passengers experience a sense of calm at altitude. There is something about flying that brings peace to some people. Perhaps it is the removal from everyday concerns, the enforced disconnection from phones and email on some flights, the impossibility of rushing off to handle some urgent matter. Perhaps it is the rhythm of the engines, their steady hum a mechanical lullaby. Perhaps it is the perspective, seeing the world from above, realizing how small our individual problems are in the grand scheme. For some, the act of sitting still for hours, watching clouds or reading or simply thinking, is meditative. Aviation is often criticized for being stressful, with security lines and delays, crowded cabins and poor food. But once the aircraft is cruising, once you are committed to the journey, there can be a surprising calm. You are not expected to be anywhere else or do anything else. You exist in this moment, in this metal tube, suspended between places, between obligations. It is a rare form of forced relaxation in our busy world. Some travelers treasure this, using flight time to think, to rest, to read books they never have time for on the ground. Children often experience their first flight with wonder. Watch children on their first flight, and you see aviation through fresh eyes. Everything is exciting, from the security screening to the boarding process, the giant aircraft, the powerful engines starting up. The acceleration of takeoff thrills them, pressed back in their seats, feeling the moment the wheels leave the ground. They press faces against windows, watching the ground fall away, exclaiming at how small everything becomes. Clouds fascinate them, and they often ask questions adults have stopped wondering about. Why is the sky blue? Where do clouds come from? How does the plane stay up? Parents, preoccupied with bags and boarding passes, sometimes miss their children's wonder. But that wonder is precious, a reminder of what aviation represents. To a child, flying is still magic, still impossible made possible. We should remember that more often. Aviation is commonplace now, routine, sometimes annoying, but it is still miraculous. We fly, humans fly. That still deserves wonder. The smell of jet fuel is distinct and memorable. Anyone who has walked across an airport ramp or stood near an aircraft recognizes the smell of jet fuel, officially called Jet A or Jet Aoni. It is sharp, slightly sweet, chemical, distinct from gasoline. It clings to clothing and hair. For many aviation professionals, pilots, mechanics, ramp workers, that smell becomes associated with their work, with airports and aircraft. Some grow to love it, finding it as comforting as others find the smell of coffee or fresh bread. It represents their workplace, their livelihood, their passion. For passengers, the smell might be noticed briefly when boarding through a jet bridge on a hot day, a whiff of the outside world of aviation. Jet fuel is a kerosene-based fuel, refined specifically for aviation, with strict quality controls. It must perform in extreme conditions, not freezing at high altitude where temperatures reach -60 degrees, not igniting too easily at ground level. It is one of the many specialized fluids that make aviation possible, as essential as hydraulic fluid and engine oil. That distinctive smell is part of aviation's sensory landscape. Aviation has its own language and culture. Pilots and controllers speak a specialized language, precise and efficient. Phrases like "cleared for takeoff," "Roger," "Wilco," and "affirmative" are instantly understood. Altitudes are stated in specific ways. Flight level 350 means 35,000 feet. Headings are magnetic bearings. Heading 270 means pointing west. This language evolved to eliminate ambiguity. In critical situations, clarity can mean the difference between safety and disaster. The culture of aviation values professionalism, competence, humility. Pilots are trained to speak up if something seems wrong, regardless of hierarchy. Co-pilots are expected to question captains if necessary. This culture grew from accidents where junior crew members noticed problems but remained silent out of deference. Now, crew resource management teaches assertiveness and communication. The culture extends beyond cockpits. Mechanics take pride in their work, knowing lives depend on it. Controllers maintain focus through long shifts. Everyone in aviation shares a commitment to safety, a seriousness of purpose balanced with camaraderie and sometimes humor. It is a culture built on responsibility. Some people collect aviation memorabilia and artifacts. Aviation inspires collectors. Some collect model aircraft, building vast collections representing different eras and airlines. Others collect airline memorabilia, vintage posters, old boarding passes, playing cards, and amenity kits from long-defunct airlines. Some seek pieces of history, fragments of famous aircraft, logbooks of famous pilots, instruments from historic planes. Aviation museums preserve larger artifacts, entire aircraft, engines, uniforms, documents. These collections preserve aviation's history, remembering airlines that have merged or failed, aircraft types no longer flown, an era when flying was more glamorous, less hurried. For collectors, each item represents a story, a connection to the past. A DC-3 model might represent the aircraft that opened commercial aviation. A Concorde boarding pass represents supersonic travel's brief era. A pilot's logbook filled with handwritten entries represents a career in the skies. These objects are more than nostalgia. They are tangible links to a story still being written, reminders of how far aviation has come and how much it has achieved. Through them, we remember and honor those who made flight possible. Aviation photography captures stunning images. Photographers specialize in aviation, capturing aircraft in flight, on the ground, in dramatic lighting. They chase aircraft to interesting locations, photograph rare types, document airlines and paint schemes before they change. The best aviation photographs are stunning. Aircraft silhouetted against colorful sunsets, breaking through cloud layers, landing in dramatic crosswinds, parked against mountain backdrops. These images celebrate aviation's beauty, the graceful lines of a wing, the power of an engine, the drama of flight. They are shared online, published in magazines, collected by enthusiasts. Aviation photographers are dedicated, sometimes waiting hours for the perfect light, tracking rare aircraft across continents, learning schedules and routes. Their work documents an industry constantly changing, preserving images of aircraft and airlines that will one day exist only in photographs. For those who love aviation, these images inspire, reminding them why they are fascinated by flight. Each photograph is a frozen moment, capturing something fleeting, celebrating something extraordinary. The sound of a Rolls-Royce Merlin engine is unforgettable. While modern turbojets are efficient and powerful, older aircraft had character in their sounds. The Rolls-Royce Merlin engine powered Spitfires, Mustangs, and Lancasters during World War II, and its sound is legendary. A deep, throaty roar, rising to a crescendo as the aircraft accelerates, changing pitch as the propeller bites the air. Aviation enthusiasts can recognize a Merlin engine by sound alone. Air shows sometimes feature vintage aircraft with these engines, and when they start up, people stop to listen. It is a sound from history, from an era when aviation was young and desperate, when these engines powered aircraft defending freedom. Hearing one today is emotional, connecting us to that history. Similarly, the sound of a radial engine, used on aircraft like the DC-3, is distinct, a rhythmic thump as pistons fire in sequence. These sounds are part of aviation's heritage, sounds that older generations remember, that younger generations can experience at museums and air shows, keeping history alive through sound. Air shows celebrate the joy and wonder of flight. Around the world, air shows draw crowds who gather to watch aircraft perform. Military jets scream past in tight formations, trailing colored smoke. Vintage warbirds lumber through the sky, their propellers glinting. Stunt pilots twist and roll, defying gravity with maneuvers that seem impossible. The roar of engines, the smell of fuel and smoke, the sight of aircraft pushing the boundaries of what is possible, it is intoxicating. Children sit on parents' shoulders, pointing at the sky. Veterans remember flying aircraft now in museums. Pilots and enthusiasts geek out over technical details. For a few hours, everyone is united in appreciation of flight. Air shows are celebrations, reminders that aviation is not just transportation, but inspiration. They honor the past, showcase the present, hint at the future. They bring together people who might otherwise never meet, united by shared wonder. They are loud, crowded, sometimes hot or rainy, but magical nonetheless. They are reminders that despite aviation becoming routine, it remains extraordinary, worthy of celebration. Some people overcome fear of flying and discover they love it. Many people fear flying, which is understandable. Humans did not evolve to be in the air, and flying can feel unnatural. Turbulence is unsettling. The lack of control is uncomfortable. But many who face their fear and fly anyway discover something surprising. They love it. They realize that the fear was worse than the reality. They find that flying is smooth, comfortable, safe. They discover the joy of looking out the window, of watching the world from above. Some even become aviation enthusiasts, learning about aircraft, following airlines, taking flights just for the experience. This transformation is beautiful, moving from fear to fascination. It is a reminder that fears can be overcome, that what we avoid might bring us joy if we face it. Aviation has converted many skeptics into fans simply by showing them that flight, while counterintuitive, is safe and remarkable. The journey from white-knuckled terror to relaxed enjoyment is one many travelers have taken, and it opens up the world. There is romance in the idea of faraway places. Flight enables travel, but more than that, it enables dreams. Looking at a departure board listing destinations, New York, London, Tokyo, Sydney, is to see possibilities. Each name represents a place you could be in hours, a different culture, different language, different experiences, waiting. Aviation has made the world accessible in ways that previous generations could barely imagine. Your grandparents might have never left their home country. You can visit another continent on a long weekend. This accessibility has risks: homogenization, over-tourism, environmental impact. But it also brings profound benefits: understanding between cultures, personal growth through travel, families and friends across oceans. The romance of distant places is ancient, but aviation has made it achievable. The magic carpet of legend is real now, made of aluminum and composites, powered by jet engines. It does not require spells or wishes, just a ticket and the courage to step aboard. Every flight is an adventure, a journey into the unknown, a chance to see the world from new perspectives, both literal and figurative. Flying represents human ambition and achievement. When you fly, you participate in something extraordinary. Aviation is one of humanity's greatest achievements, a testament to our curiosity, ingenuity, and refusal to accept limitations. For thousands of years, we looked at birds and dreamed. Then, barely more than a century ago, we made it real. Within a single lifetime, we went from the Wright brothers' 12-second flight to jumbo jets carrying hundreds of passengers across oceans. We went from barnstormers to moon landings, from wood and fabric biplanes to supersonic fighters. This progression is breathtaking. Aviation pushed forward countless other technologies: materials, science, computers, navigation, weather forecasting. It connected the world, shrank distances, opened possibilities. It represents what humans can do when we work together, when we refuse to give up despite failures and setbacks, when we dream of impossible things and make them real. Every time you board an aircraft, you are part of that story, benefiting from the work of thousands who came before, engineers and pilots and dreamers who looked up and said, "We can do that." Flying is not just transportation, it is triumph. Conclusion. And so, dear listener, our journey through the world of aviation comes to a close. From the earliest dreams of flight sketched in Leonardo's notebooks, to the Wright brothers' fragile flyer lifting off the sands of Kitty Hawk, to the mighty jets that now cross oceans, carrying hundreds of people in comfort and safety. We have explored the science that makes flight possible, the elegant dance of lift and thrust, drag and weight, all balanced in perfect harmony. We have marveled at the engineering, the powerful engines, the sophisticated systems, the attention to detail that makes modern aircraft so reliable. We have honored the people, the pilots and flight attendants, the mechanics and controllers, all the countless individuals who work together to make flight safe and routine. Aviation is a story still being written. Each day, new technologies are tested, new routes are opened, new aircraft take to the skies. The future may bring electric propulsion, sustainable fuels, even supersonic travel again. Or it may bring changes we cannot yet imagine, innovations that will make today's aircraft seem as primitive as the Wright Flyer seems to us. But whatever the future holds, aviation will remain a testament to human possibility, proof that when we dare to dream, when we refuse to accept that something is impossible, we can achieve miracles. As you lie here, letting your breath fall into an easy rhythm, imagine yourself aboard an aircraft, not anxiously, but peacefully. Picture the smooth acceleration of takeoff, the gentle press back into your seat as the aircraft climbs. Feel the moment the wheels leave the ground, that magical instant of transition from earth to sky. Watch through the window as the world falls away, as houses and cars shrink to toys, as the curve of the horizon appears. Climb through clouds, emerging into clear blue sky. Look down at the white landscape of cloud tops, stretching endlessly. Feel the steady rhythm of the engines, that constant hum that speaks of controlled power, of systems working in harmony. Imagine cruising high above the earth, suspended between ground and space, moving across the sky at hundreds of miles per hour, yet feeling almost still. The sun shining bright, the sky that perfect blue that exists only at altitude, time passing gently, the world below scrolling by unseen beneath the clouds. Then the gentle descent, sinking back through the clouds, the ground reappearing, growing larger, clearer, the runway approaching, the touchdown, smooth and controlled, the roar of reverse thrust, the deceleration, rolling to a stop, engines spooling down, the journey complete. Every flight is a small miracle, a routine miracle perhaps, but miraculous nonetheless. Every time an aircraft lifts into the air, it proves again that humans can fly, that the impossible has become possible, that our dreams can take physical form. Flight connects us, brings us together, opens the world. It is adventure and routine, prosaic and profound, all at once. If you happen to still be awake, you can rest now knowing that above you, at this very moment, aircraft are tracing paths across the night sky, carrying people toward their destinations, toward reunions and adventures, toward home and toward the unknown. The world of flight continues, day and night, a vast network of movement and possibility. But if your eyes are growing heavy, let the gentle rhythm of aviation carry you into rest. Close your eyes, breathe deeply, and drift into sleep, into stillness, into the peaceful sky where all flights end safely, where all journeys reach their destinations. Good night and good flying.